Okay, we are live on YouTube, so we are set to go there. Hi, Risa. Risa is an EPSP Connects organizer. She's going to help out just monitoring the Q&A and the chat. Danica, are you talking about how people can enter questions, or am I doing that? I guess I'll do that.
You can cover that, yeah.
Okay, and I'll do that in my second thing. Okay, great. So folks are here. So we'll let people trickle in for another minute or so, and then we can get started. I usually have my dual monitor set up. It's very hard to get all the windows in the right place on just a tiny laptop screen. All right, so it is 8 o'clock, so I think we should just get started. Everybody ready? All right, great. So welcome everybody to this EPSP Connects special event focused on applications of environmental seismology and distributed acoustic systems, or DAS, to geomorphology, where we have a great set of panelists here today to talk about the intersection of geophysics and geomorphology in an event that's partnered with the DAS RCN and led by the Geomorphology Working Group that is co-led by myself and Danica Roth. And so Danica is going to start with a quick description of what that DAS RCN is doing. Take it away, Danica.
Thanks, Claire. Okay, so for some context on this, as like Claire mentioned, we're leading the Geomorphology Working Group for an NSF-funded research coordination network on distributed acoustic sensing, or DAS. So we'll talk a lot more about this, but DAS is basically a fiber optic seismometer. It's got a lot of potential for monitoring and characterizing surface processes at really high resolution. I'll put a link in the chat in a moment to the RCN. So NSF and GLD are very supportive of the RCN's broader goal to facilitate increased use of DAS in the geosciences. And our working group is tasked with identifying applications, needs, and challenges with using DAS instruments in geomorphology. So we've identified a few major barriers that currently limit the surface process community's engagement, not just with DAS, but with environmental seismology overall, which we've kind of distilled down to 3 broad categories of what is DAS, how do we access and deploy instruments, seismic and DAS instruments, and what do we do with all the data we collect. So the goal of this panel discussion is to raise awareness and excitement about the opportunities provided by DAS and other seismic instruments, and to start surveying and addressing some of the specific needs, challenges, and obstacles to using these tools in our community. So we will also have a virtual community forum on June 9th to continue this discussion and solicit more detailed feedback from anyone who's interested. So keep an eye out for that announcement. And I think that's all I have. So I'll hand it back to Claire to get started on the panel.
Okay, great. So yeah, like Danica said, we're here for the next hour to chat with our great panelists about the applications of DAS and environmental seismology to surface processes. And we have a few questions, like Danica said, that we're going to start with our panelists, but then we will open the floor to everyone else on the call. And so we encourage you, when you ask questions, to use the Q&A function in the Zoom webinar. But you can also look through the chat where our panelists will be posting resources and links, and feel free to also have some conversation there. But in terms of getting your questions flagged, the Q&A is really the best place to put those, to make sure that we see them. And so to kick it off, we're just going to ask each of our panelists to spend 1 or 2 minutes introducing themselves, their background, and any experience that they have with either DAS or environmental seismology. And so let's start with Michaela.
Thank you. So hello, everyone. My name is Michaela. I'm a PhD student at ETH Zurich in environmental seismology. My background is actually seismology, so I did a geophysics master's beforehand, and then jumped directly into environmental seismology. So mostly we're monitoring and detecting mass movements with seismometers. However, my group has been transitioning a bit into working with DAS. So I don't have I have general experience with DAS, but I have never worked with actual DAS data.
Thanks, Michaela. We can go to Eileen next.
Thanks. I'm Eileen Martin. I'm an assistant professor at Virginia Tech I'm an assistant professor at Virginia Tech in the math department and computational modeling data analytics program. I've been working with DAS data since about 2014 on a variety of different problems in near surface geophysics, doing urban seismology, working a little bit with earthquake hazards, some permafrost thaw monitoring more recently, had some great collaborators at ETH Zurich who've been sharing data with me on glacier monitoring and trying to learn about those kinds of processes. So some connections to environmental seismology as well. Yeah.
Great, thanks, Eileen. We'll go to Jin next.
Hi, thanks, Claire. My name is Ge Jin. I go by my last name, Jin. I'm an assistant professor of geophysics at Colorado School of Mines. So I started out work on not only DAS, but the distributed fiber optic sensing, including DAS, DTS, and DSS, since about 2015. So initially at the oil company, and then later in the academia. So my experience on this are more related to the oil industry application, things like microseismic monitoring, hydraulic fracture monitoring, but also quite interested in the surface process. I did my PhD on surface imaging and ambient noise tomography, so which is highly related to the near surface, and also a good application for DAS on this. So yeah, I'm willing. Thanks for inviting me for this.
Great, and we will close out with Marine.
Hello, my name is Marine Denol. I'm an assistant professor at the University of Washington. I started exploring how we can use seismic waves to probe the near surface in 2016. And I was a crustal seismologist, but I've slowly looked in shallow and shallow depth and realized how heterogeneous the geotechnical near surface environment is. And so I'm trying to probe what is that heterogeneity and the temporal variations and the impact of environmental factor on this environment. And we look using a lot of large data set, regional networks, and really long time scale. And so we're slowly getting into the scale that DAS can actually help us tackle.
All right, excellent. And so we'll kick it off now with our first question to our panelists, which is, what is the general idea behind environmental seismology, and in what ways is that different from traditional seismology? And what types of environmental processes can you measure with environmental seismology? And we're going to start maybe with Michaela and Marine taking this question.
Okay, so I mean, I would say that the main idea behind environmental seismology is that we actually want to understand near surface processes. And we do not only want to understand this, but also detect those processes even and monitor what is happening. So I think detection, monitoring, and understanding are the main things about environmental seismology in general. What is maybe a bit different is that we use the same physics, or the physics behind it is the same as you would use also in normal seismology or traditional seismology. However, environmental seismology is still kind of a younger field. So for many processes, we're not even sure how these signals are generated exactly. So there is some kind of uncertainty on like what we see actually on our seismic data, which of course we also have in traditional seismology, don't understand me wrong. But I think that this is a bit of a difference that for traditional seismology, we normally, when we have an earthquake signal, we, for example, can look at different arrival times or different phases that arrive or that we see in the seismogram. However, for many processes in environmental seismology, we basically just have larger amplitudes and we're not really sure where this is coming from. So I think this is one of the main differences or challenges that we are facing in environmental seismology.
Yeah, so that's a great definition. I'd like to add on Michaela's point that it used to be that these would be noise signals. And the Pacific Northwest is historically famous for studying exotic events that are basically everything that's labeled as noise because the river is too loud, there's a glacier that's sliding, there's a rock fall, and conventional seismologists would just say, please mute this so I can focus on earthquake signals. And so now this is just looking back and saying, well, there's a lot of signals that have the same physics as what we expect from wave propagation for normal earthquakes. But this time we want to understand how they're impacted by these non-conventional conventions evolve with time. So maybe they will become conventional signals eventually. And then the other aspect I'd like to add is on the ground motion aspect, we tend to think about ground motion as having a side effect, which is just a term, literally a term that says the amplitude will be enhanced or decreased depending on the side effect. That is actually entirely motivated by or explained by wave propagation in non-consolidated soils, which is where wave propagation becomes nonlinear. We don't understand, there's water, it's drying, there's no cohesion. This is basically capturing a really vibrant material that is impacted by environment, but we cannot yet predict what this term is. And so the conventional seismologists just put that into a side effect term. So the idea is we could actually go back to conventional seismology, but try to understand the relation between the environment and this surface structure.
Great, thank you. Eileen or Jin, anything else to add?
No, I think that was a really good explanation.
Yeah, that was really nicely explained. Thank you both.
So we'll move on to our next question, which will start with Jin and Eileen. So what is DAS? How is it different from more traditional seismic setups? Why might it be a good tool for more environmental applications?
Yeah, I'll start us off with kind of a basic explanation of it that just at a very high level, you can think about just having sort of an optical system at one end, and that's also got your power source and everything, your data collection is going on there. And then it's plugged into this fiber optic cable that oftentimes is just a standard telecom type fiber optic. Sometimes you buy specialized ones, but usually it's just a regular one. Then this single interrogator unit is probing this fiber optic cable with a laser. Energy travels along it and gets backscattered, just a very, very tiny proportion at each location. And from one ping of the laser to the next ping, we look at how does that profile of backscattered light change? And if the profile is changing at a particular time of how long it took the light to return to that interrogator unit, that's our optical system, then we can kind of infer based on what the speed of light in a fiber is, where that profile was changing spatially along the fiber. And then we infer, okay, this is where our fiber is getting stretched or compressed. And so with that, we're able to take that fiber, turn it into a bunch of really densely spaced, basically strain or strain rate sensors, depending on the system. And then we're able to get a time series at each one of those locations along the fiber. Just by changing our optical settings at that interrogator unit, we can suddenly turn this into hundreds or thousands of sensors. So big picture, I think those are kind of the big things. There's a lot of details of working with strains or strain rates that are different from working with velocities or accelerations for seismologists, but I think those are more in the weeds kinds of details.
Yeah, so also I would like to add on like why DAS is specifically really good for environmental seismology, is that this is actually, just as Eileen said, is a good technology actually separate the sensing part from the data acquisition part. So the data acquisition part is just a optical box and as large as a workstation. And then you plug the fiber into it, and then you convert this fiber, can be up to 10 kilometers long, into an array of very dense deployed sensors that with a very high temporal, spatial and temporal resolution. And the fiber cable that you can purchase just off the shelf, they are very cheap. You know, even the really tough mineral-based one, they're only a little bit more than around $2 per meter, compared to hundreds of dollars or thousands of dollars per sensor that you usually have. And also this cable can really endure very tough environment because they are actually built up for internet transportation. They are built up for burying in the ground and can survive for more than 10 years. So once you deploy this fiber into the places you would like it to, you don't need to worry too much about it. I heard that there were some animal like to chewing it. So if you bury it, it should be fine. But that is really designed to survive a tough environment long term. And also is actually have the other good thing is, you know, this cable, along the cable, we have really, really dense spatial resolution. So this is particularly useful, especially if you don't really know, you know, as a purist discussion that a lot of the challenging part is we see signal, and it could be signal, it could be noise, but we don't really know where it's coming from. We don't really know what's causing it. However, if you have a very dense array, you can really see that where that wave coming from, how the wave propagates. So you can tell what type of wave it is, what kind of a source is it. And that's actually bring up a lot of insight and gave you the answer and easily gave you the answer that what's causing it. It could be a river, it could be a landslide, or it could be just a car that passing by. So we can really tell the difference.
Thanks. Do Michaela or Maureen, do you have anything else you want to add?
Maybe one small thing, which I'm not even, like, as I said, I'm not an expert in DAS, but I think what I realized is that sometimes the signal to noise ratio for DAS is not as good as you would have maybe for a broadband seismometer or a really expensive seismometer. But I think often in environmental seismology, this is actually not super important. So of course, the better it is, I mean, the better the signal to noise ratio, the better it is for our analysis. But I think for many processes we're actually looking at, we don't need the best signal to noise ratio in environmental seismology because we're not looking for micro earthquakes or something, you know, like really hard to find in the data. Or quite often, I mean, of course, there's cases where they need to have a really good signal to noise ratio, but generally. So I think for this also DAS seems to be quite helpful in environmental seismology.
Thanks.
Can I just add on that? It's very interesting because signal to noise ratio is, and the way to increase it and the noise it is a hot topic in machine learning. And it seems that thanks to the density of these measurements along the cable, there's a lot of spatial correlations in these waves. That's how you get move outs. And so there's actually tremendous progress in denosing and using this, even if it's noisy, you can still leverage the density of these measurements to denose using normal and fancy methods.
I also want to add on to this in a way that, of course, right now, if you just use a normal telecommunication fiber, use a low-end or mid-tier DAS box, you do have, experience 5 to 10 dB more noisy data that compared to a geophone or broadband seismometers. However, if you are good on budget and you use specialized fiber, which are designed for this type of sensing, and then you use the top tier interrogator, right now, actually, the noise floor is only 1 to 2 dB less than a state-of-art geophone. And then you consider actually you have a very dense spatial resolution. So basically it means that I can stacking 5 to 10 channels to replace one geophone. And then you can actually get as good as a geophone or even better. So the main constraint I consider that the DAS have currently is actually it's a single component sensor. So it can only sensing the strain change that along the fiber direction versus a broadband seismometer or geophone, you actually have a 3-component measurement at a single point. So that's actually a lot of affecting factor, and currently there's no good solution on that yet.
Yeah, one of the systems Jin and I have used, actually, you can drop a cotton ball in the lab and it'll pick it up. So very sensitive for certain systems.
Just to clarify for anyone who is wondering what dB means, decibel, so log 10 system.
Thanks, Danica.
Okay, so we'll move on to our next question for Michaela and Eileen. And so we talked already about how environmental seismology picks up signals of events like sliding glaciers or landslides. And so what type, beyond just detecting when these events happen, what other types of information about these processes can you get from different aspects of your seismic signals?
Okay, so I mean, there's like a super broad spectrum of things you can observe with environmental seismology. If we start out in more cryosphere, then we can actually, as you said, have a look at how the glacier is sliding. So this is something that we normally can't, because we can't not look into the glacier. We can, so it's a bit similar than looking into the earth, but now we're actually looking at the interface between bedrock and the glacier, which seismology allows us to do. But we can also monitor, for example, the water content. So we can monitor melt, which is really important for glaciologists. Or we can actually monitor glacier calving, so when icebergs break off and what kind of mechanisms that they have. And this is, of course, again, making the bridge to sea level rise very important now for Antarctica, for example, to have a look at this and maybe find precursors and these kind of things. If we then go to permafrost, we can also have a look there, how permafrost changes in the mountains. And permafrost, of course, also influences rock stability, which is also something that we can actually have a look at, not only related to permafrost, but also generally on some rock slopes. You can have a look at how stable this rock is and how the cracks evolve over time. So this is really good into looking into what is actually happening in the media, and not only seeing what we can see with cameras or a radar. And then, this already transitions to landslide monitoring, of course.
Yeah, I think one of the other things is just there's this whole world of array processing that I think a lot of times many environmental seismology studies are just using a small collection of sensors. And so with DAS, it really makes it easier to do the deployment of a large dense array. And there's a whole new suite of methods that are available to people. So there's been quite a few advances in the last couple of years on beamforming with DAS arrays out of, I think Martin van den End has done some work on this. There's also been some work out of National University of Singapore on this, just improving our methods for figuring out basically what direction our sources are coming from based on just a small dense array. There's also been a fair amount of work on trying to estimate seismic velocities, either through ambient seismic noise or through active recordings of signals, based on array processing with that, mostly tomography based. And so I think that with those, you're able to say, where are the sources? Also, how fast are they traveling through the ground? What is that ground structure? Like, I think Maureen was mentioning this earlier about trying to understand the structure. And so those array processing techniques that are opened up by DAS are really very powerful for that. There's also, some aspects of really understanding what the source mechanism is that I think are a lot more promising with some DAS recordings in there. So like just a simple example, like let's say up in Alaska, we were trying to study some permafrost thaw, and we saw that it was near a road, and you could see not only like what is the speed of the car traveling by, when is it going past each of the sensors, but as it hit different road joints, you could then see smaller sort of parabolas of seismic energy and try to know like from that you could actually see like what would be the move outs from those. So there's things like that where you can just see smaller details within your sources. And I know there are other people that are working on sort of true source inversions with DAS data. So that's another direction to keep an eye on, because I think that that's going to give a lot more information in the near future about what is the actual source mechanism, where it's actually happening.
Great, thank you. Maureen or Jin, anything else to add here?
Oh, should we talk about flow rates being something that can maybe be estimated with DAS? Jean has a lot of experience on that with laboratory experiments. And I think, Danica, you did some like river experiments, right?
Yeah, whatever you can measure, I think people want to know about it.
Yeah, we were just, Danica and I were just talking about this almost like last week, I believe. And we are able to measure flow rate in the pipe in the lab. So there's a lot of oil industry application that we wrap the fiber around the pipe, around the pipeline, and we can monitor flow rate inside. And I believe a similar concept can be done in the river. However, it does require some special setup on the fiber and on the instrument. However, it's because the fiber are pretty tough, and we can just not like a normal sensor, you have to be carefully maintaining it. Fiber, you can really torture it. So Danica and I were even thinking about actually we design some fiber setup so we can just drop it in the river and monitor flow along the river at different points. So that's I think this is possible, but it hasn't been proved yet, I would say.
I'm not a panelist, but I'll just say that there's been some kind of more broadband seismology work done on trying to monitor fluvial flow. And there's some theoretical models. You could, it was Misha Dietz in Germany, just put out a R package, I think, called EnviroSize or eSize. Sorry, I'm forgetting all the names, but got some usable tools for broadly monitoring and inverting for physical characteristics.
All right, well, shall we move on to our next question?
All right. Okay, so if I'm going out to the field to study whatever my geomorphic process is, what should I be thinking about or considering to assess whether or not seismology is something that could help me? And in what scenarios would DAS or other instruments like broadband seismometers, 3-component geophones, where would they be the best option?
So I can get started. I'd like to give a specific example, which I have never done myself, but I'm thinking about how we can get subsurface structure and the time dependence of it in places that are either too dangerous to go deploy, or the vegetation is too high to use any kind of satellite imaging techniques. And I feel like the combination of DAS with 3-component sensor to give you the as much of the 3D wave field as possible is a great tool to understand or to monitor the subsurface. It will be very interesting. So let's say it's a rainforest landslide area in the Pacific Northwest. it's a little bit sketchy to go deploy a lot of sensors like geophones or broadband, so you don't want to spend too much time on it. The time to deploy a fiber is really short, so you minimize risk that way. You also enable the localization of cracks and shear focused deformation. So if you have the onset of fracture is something that you could have a cable going above, and you would be able to see that by probing, either by listening the cracks itself or by probing the structure using techniques that we just discussed, while minimizing the risk. And so deploying a few other broadbands would help also, so then get the 3D wave field. But Rick was pointing one of the issues also potentially with this is the idea of having a good transfer function of once you have these measurements, how do you turn that into motions and what are the actual amplitudes? And the advantage of using conventional, a few, sparsely spaced seismometers will allow you to calibrate your amplitude to get actual, true ground motion. So in that sense, I feel like that's a wonderful thing. I'd like to bring something that's maybe a little bit more urban, but it occurs to me that you can monitor structure like dams and bridges because cables are already in place. And I think in city like Seattle that refuses to assess how much they have to spend to fix the bridge in case of something and the West Seattle Bridge collapse. There's a lot of room for using that to also help understand material properties, material damage, both in the soil and in the structure.
Yeah, so I would also like to add on that because the fiber itself is really thin, so the fiber itself is just as thin as your hair. That's where the light actually transfer and where the instrument really care. So you can easily put in like 5-10 different fibers into the same cable that you deploy, and with a minimum increase of the cost. And now if you have deployed a cable that with multiple fiber in there, don't think about just adding dust to it. You can measure distributed temperature at the same time, and you can measure distributed strain change along the fiber at the same time as well. So that's basically just converting the same cable that you deploy into 3 group of distributed sensors: temperature, static strain, and also dust, which sometimes we call the vibration sensor or dynamic strain sensor. So combining all this information together can really bring you insight of what exactly happening. Yeah, I don't know, can I share a screen for one slide really quick? Okay, yeah, so I just want to show one of the publication that it's not mine, but I really like it. So this is actually a pipeline monitoring system using both the DTS and the DSS, distributed string sensing. So you can see using the same cable, and what you're showing here on the top is actually a string build-up event across a whole month of a landsliding event. Actually, you can see the result of that at the bottom. So you can really see this gave you a very dense sampling on both spatial and temporal. And you can really see how this deformation of the ground building up through months. And you can see in terms of time, this is a little bit more than, actually almost 2 months in spirit. And with a point sensor, you will be extremely lucky that you can caught that. But using the distributed sensing, you can actually deploy this thing. And the data are limited to 10 kilometers, but DTS and DSS, you can go up to 100 kilometers. That you can really mapping this and waiting for the event to happen. So I think this is this is a great thing that could be of interest for many scientists in this field.
Eileen and Michaela, do you want to add anything?
Okay, great. So potentially some of our viewers today are now inspired to go and plan their own deployment for the first time. So what should first-time users know about planning their deployments and working with seismic data? So how do you get instruments? What types of data volumes should you be prepared for? How could you access or archive existing data, existing tools for analysis, and what are some of the most common pitfalls that new collectors or users of seismic data might run into? And so we'll start with Michaela for this and then open it to all of our panelists.
Okay, so I will mostly focus on setting up the seismic array because I don't know much about the DAS setup. But generally, I would say the most important question is, what do I actually want to see? So from my experience, it's always a bad idea to just, I have like an instrument, let's just put it there and see what happens, which can be very good, but also I think it's very important to have a bit of an idea what you want to do. So depending on if you want to, for example, localize an event, or if you want to have a look at how, I don't know, a debris flow is flowing down a channel, you would definitely set up your array a bit differently. On the same line of thought, like is that you need to have a look at what kind of frequencies you're expecting. So of course, no one of us wants to have like a huge amount of data, so you cannot just sample. I mean, you can, but it's maybe not the best idea to just sample with like, I don't know, 2000 hertz or even higher than that, because actually generally we're not even interested in those kind of frequencies or the high frequencies. So maybe if you're like really doing this the first time, have a look at some papers, see how, like, in what frequency range you're looking at, like the process you're looking at, and then use just like, like something that would allow you to do your monitoring or whatever you want to do, but not use too much space for just saving the data even, or just like reading it is really annoying if you have a lot of data. So yeah, so I think these are like one of the most important things. In terms of like size or what you should expect from a deployment, I can only for example, a day of one component sampled at 100 hertz would be like 8 megabytes of data. So it's actually not an insane amount, especially comparing to DAS data that you get, for example. And then if you have an array of like 5 to 8 stations, you'll see that you generally don't get, like, you get several gigabytes, but it's nothing that is, too much to store locally or something. So that is actually very easy. And then the pitfalls, I think, are actually one of the most important things. So as I mentioned already, the network setup is very important. Then you have to look at what sampling rate you go in. And then, of course, the sensor installation itself. It's very important that it's coupled to the ground. So you need to have it leveled, for example, and then have a good coupling. Yeah. So that if, like, for example, some wind comes in, also that there's not too much noise of, some other environmental factors or just temperature or something. So generally burying it into the ground is a good idea. However, I would say if you do this the first time, maybe it's good to bring someone who has done that before, or collaborate with just, your seismic group that is in your university. Because I think generally seismologists are getting more and more interested in environmental seismology. And I'm sure if you're a geomorphologist and you're looking for some seismic data, I'm sure they'll be happy to help. And this is also where you get your instruments from. And yeah, of course, and then it's important also to know what your instrument actually does. So generally what we get is actually a digital, like some output from a digitizer, so you don't get the ground motion right away. So you need to correct for the instrument response. And this is very important that you actually know what you buried into the ground and know what your digitizer does also to actually take care of that. And then there's, of course, processing artifacts. And for that, I'm always a bit advocate of using Python to work with seismic data. And there's actually a super nice website online, which is called seismolife.org. If you're new to seismic data, this is definitely like the way to go. I'm just going to put it in the chat very quickly. And you can look at Jupyter notebooks, and literally anything from getting your data to how to process them is super nicely explained there. So I would recommend that to everyone who's in seismology for the first time. Yeah, I think that's basically it.
May I add to this? I'm not afraid of data personally, and so in my experience, we did not know what frequencies we should have been looking at when we did a controlled groundwater monitoring experiment. So we did not sample at rates high enough. and that just like killed the project. And so I'd rather personally collect more data than not enough. And it's feasible to downscale afterwards. In my experience, storage is cheap, but I understand there's some limitation, especially with DAS. But nowadays, you can get terabytes of storage for $100. It's not that expensive. The reading of these, so there's different scales of your problem. If you look at that megabytes or gigabytes, Python is great. Moving up, you will run into really fun problems of large scale processing. And I am not a big fan of Python when we get to that scale. So I'm trying to explore other languages like Julia to help mitigate that. Another thing I'd like to add on the experiments is the care in writing down the location, the environment around the sensor. The coupling is number one. The presence of trees might bring you a different frequency content locally to your station. It does not mean it relates to the source. It will be really fun to add on a MET station to really understand temperature effects, precipitation. And I think one of the struggle that the archive, seismic archive, geodetic archives, all of this, is that the instrumentation is not really comprehensive across fields. We don't have an accurate GPS co-located with the seismometer, co-located with the MET station. And so we always try to understand, to find what value these are based on other archives. And so we think about interpolation a lot. But in the ideal world, in the future, our observatories, temporary observatories, would have all kinds of measurements at once. I think that's the big limitation. Going back in the past is kind of playing and interpolating, but in the future, I think it should be way easier to just put that together.
Yeah, I would like to add on that, because I actually deploy a lot of DAS arrays, and but just don't be afraid of DAS array. Actually, deploying a DAS array is a lot of time much easier than deploy a broadband seismometers. I did that a lot during my PhD and master time as well. So actually, I was just coming back from the field camp of our department, and the student deployed the DAS array every morning and within an hour. So they deploy like 1 kilometer line, and then it's take us about half hour to connect it to the machine and start recording. Each day we generate about 120 gigabytes of data. And so it's actually much easier nowadays. And the DAS box has been manufactured in a way it's very compact. So actually tomorrow I'm driving to Wyoming, throw the DAS cable in the lake, and just put the instrument in my car, have 1 kilowatt generator to run overnight and record the lake for one night. And that's basically just can be done by a 2 people team. And we plan to use our stand-up paddleboard to actually retrieve the cable. I'll tell you how fun that will be afterwards. But basically, the whole setup is a very small print. And they, I actually see some, vendors from companies, people that actually are renting these DAS machines. So I think, you can, if you're interested in that, what you can do is go to the website, purchase 1 kilometer or whatever long kilometer of military-based cable, deploy it, and then talk to this company to let them bring in the machine. You rent it for a day or for a week, and that's not very costly, and you immediately got pretty good data. And then if you find something interesting, you can actually get them back or purchase your own DAS box. So I think in general, just don't be afraid of it. Just go ahead and give it a try. It's a lot of fun, actually.
Yeah, I think what Jean said about it being relatively easy to deploy is definitely true compared to, say, like when I've done node arrays. So like with a node array, you might put out all of your different sensors, and then depending on the setup of the type of nodes, you may or may not actually be able to collect your data until you go out and actually pull the data off of each sensor individually. Whereas with DAS, because you just have that one interrogator, you're also able to just plug in a computer monitor to that for most of the interrogators that I've used, where you just see like basically a display of how much energy is there integrated over certain frequency bands that you think are most interesting. And so you can just visualize your data in these kind of waterfall plots and see at different locations how that spectrum of energy might be changing. And that can also help you while you're in the field to make sure that if there are spots that have, a lot more noise than you would expect, you can kind of pinpoint where are those and decide whether you want to adapt your deployment in the field as you're out there. I think one thing that Maureen mentioned about the locations is really important. Being able to, once you throw your fiber out there, you don't have locations on each of your sensors. You just here's the distance along this fiber that might be going through some very windy path. And so a lot of us do this process that we call tap tests. And you go along the fiber, hit the ground, or maybe stretch the fiber at a known point in time. So you write down when you do it and where you're doing it. And then you can track it back when you look at your data to what is the sensor number or the location along the fiber that you actually picked up that signal at. So that's something that I think is quite different for people who are used to maybe working with just point sensors. On the data side, last year, Nate Lindsay and I put together a series of like Jupyter notebooks, and there's also a talk by Nicole Taverna over at National Renewable Energy Lab on using notebooks to interface with the geothermal data repository, which is hosted on AWS, just so that people can have some basic examples of some open source data to start playing with before you go out and collect your own. It can help you also just get a sense for yourself, if you're not used to working with seismic data, of how comfortable are you with working with these arrays. So these are just using sort of short time windows, but you can start to very easily think about, how could I scale this to continuous recordings over a long time period of what I think my experiment needs to be, and gauge your comfort level for whether these tools would be appropriate or if you need to start looking at other options. So hopefully people find that useful. I'll do a talk as part of the ROSES tutorials for students this summer on DAS that will go through some kind of similar tools for people that are trying to build seismology skills. So I think the registration is probably still open for that. I'm not positive, but yeah.
Thanks, Ben. We can share links to those in the chat. So I think we'll open it up to audience Q&A at this point. I might start with Suzanne Anderson's question in the chat, which I think is a good kind of starter. So Suzanne was curious about whether signals are primarily interpreted in terms of the source, like cracking or flows that are generating seismic signals, or are we using seismic signals generated somewhere to infer seismic velocity structures, like the way we do with seismic refraction studies?
I think this varies a lot. So one study I'll point to is some of the work by Tioan Zhu at Penn State on an array that was there where they were recording lightning strikes and thunder that was happening. And they're kind of looking at it as, how do you infer what that source waveform is, but then looking towards how do you use this as an energy source for imaging. So I would encourage you to take a look at that paper as one example where they're kind of looking at both sides of this issue.
Another question by, oh, sorry, Michaela, do you have a comment?
Oh, I was just going to say that maybe there is easier ways to infer something about the subsurface structure than using environmental seismology. So, I mean, generally, I think you can do that. And if you have like the data, why not? But if you're really interested in some specific parts of the structure, maybe it's easier to use active seismics, for example. Yeah, so I mean, it works, but I think it's not the easiest way to do it.
Yeah, I'd just like to add that using ambient vibrations, we can do funny things with cross correlations that would give you a signal that is an approximation to these active source surveys. So you would not necessarily do the tap test and everything. And so there is ways to do, it's subject to interpretation. There's a debate about interpretation, but I think if you just use the ambient vibrations, you could do this kind of mapping. And if looking along the cable, there's been fun studies on looking at how waves, there's reverberations of waves in fault zones that you can actually see along the cable. So I think that there's ways to extract that information. But the source and the path, all those trade-offs, so it's subject to careful analysis.
Yeah, I think it's depends on the resolution you're seeking for. So ambient noise stacking, and they can only stack out surface wave in most cases, and surface wave have a certain resolution and frequency band. If you're looking at some reflection depths, or you're looking at really fine structure, and the active story will give you a much higher frequency, which means much shorter wavelengths or much higher spatial resolution. So what source you bring in, whether you bring a source or not, is highly dependent on what type of question you're trying to get out of this data.
All right, so I'll move on to the next question. From David Hill, what is the typical bandwidth of the data required for environmental seismology, which I imagine we might have very different answers.
As broad as you can. We're looking into strains that are really long period and 2 kilohertz seismicity in glaciers. So that's why it's great about DAS, I think, is that bandwidth. Which is needed for seismometers. Mm-hmm.
I'm sorry, Mary. Yeah, so I would like to make some comments on this. Is that DAS, it is broadband, so you can actually measure some millihertz. So in the oil industry, we actually see convert it into a string sensor that see the growth of hydraulic fractures, which have the period of hours, sometimes even to days. You can also look at the very high frequency. So unlike a broadband geophone that you actually have a peak response and then it dies out from both ends, does actually have a very flat response in terms of frequency. But keep one thing in mind, that flat response in the frequency is in the string rate domain. So if you're talking about the propagating wave, so this is a little bit about Fourier transform, but you're talking about propagating wave, you actually have a decreased sensitivity towards the low end, because you need to integrate the string rate to get the particle motion, and that integration serves as a high pass filter for the data. So it's again depends on what type of signal you're looking at, and then you talk about what type of frequency band it is sensitive to.
So we had another question from Rick Astor. Another issue for some applications may be the transfer function, including the gain, which for non-seismologists is the function that describes how you go from the seismic wave to what you actually read on the seismometer. Since that will relate to mechanical coupling between the instrument and the ground and other factors, how well can co-deployment of seismometers at a few points provide a robust empirical transfer function that can be usefully interpolated across a fiber?
Did Rick answer his questions? No way.
I think Eileen is probably a good one to answer this question. She did a lot of comparison.
So I think there's a good paper by Patrick Peitz that focuses on across a pretty broad range of frequency scales and different experiments with different types of coupling and deployment conditions, where he was looking at this question of getting really clear quantified comparisons there on sort of how good is the phase and also the amplitude across these different frequencies. And so I'm blanking on which journal this was in, but if you look at Patrick Peitz's paper, there's one that's 15 octaves of this kind of comparison or something like that. And I just think it's a great reference for this question.
I also made Lindsay's in GGI paper, I believe, also talk about that. But one thing just from the fiber side, so what it does is measuring is actually string rate be applied to that fiber that bury inside your cable and bury inside your dirt or material that you're asking. But the instrument can actually give you the absolute string or string rate measurement on that fiber core. And how that related to the actual string that applied in your material, that depend on the mechanical coupling between the outside and to that fiber core. While also keep in mind that can change from location to location. You may have a compacted dirt versus a more loosely less compacted dirt just next to each other. So your string transfer function could be very different. However, the instrument itself can give you the absolute, you can convert that into absolute string of the fiber core directly. That's actually fairly accurate.
Okay, great. And it seems like, so there was a request in the chat for any references, if people can throw them in there. We can also post those on our EPSP Connects webpage after this for people to access. So we'll take one more question. This one is from Nancy Ingabire Abayo, and she is asking for advice for what kinds of techniques you would recommend to effectively capture the angle of inclined deposits in modern meandering rivers. So inclined strata, barocliniforms, and similarly, if there are recommended techniques that can capture the differences in the deposits based on their age. So any ideas on how you would tackle this problem or this research question?
I think one fundamental limitation of seismology in making this inference is we really rely on seismic impedance contrast. And so lithology that are different do not have actually difference in impedance contrast. We're not going to be sensitive to these changes. And instead we may seek just something that's blurred. And so in a way, I would think that there's a potential for DAS and kind of like this ambient vibration analysis on single channel. I can get into the details, but you can do some kind of active, pseudo-active surveys to that, but it will still rely on having contrast of lithology, which I think may happen in context of active deposits and events of, I'm not a geomorphologist, but you see my point, like when you clean up the surface and then you add on, like it must be contrasting. And I have seen in other environments in alluvial fans that after an earthquake, we could see actually new reflectors showing up in these functions that we interpreted as being a change in the grain arrangements. So I think it is possible, but it does rely on that. And my interpretation may be wrong, but it does rely on that contrast in seismic properties.
Okay, great. Thanks, Maureen, for that. Okay, so in the interest of time, we are going to start wrapping up. And so my final question to our panelists is there anything that you would like to plug right now that you think is particularly interesting, events coming up, resources, anything that you want to plug? Now is the time.
So there's a workshop coming up in August as part of the SAGE Gauge workshop that's focused on DAS, and it's run through the DAS Research Coordination Network. And we're trying to especially highlight talks that have some kind of bridge between the seismology and geodesy communities. So it doesn't have to totally bridge that, but if you have something that kind of gets at those connections between those two communities, we would love to have talks in that direction. So I'm gonna post the link here. And then if you go into the additional information, there's a link to a Google form where you can submit either a lightning talk or submit to be considered for a full-length talk. So hopefully I'll see some of you all there. And then there's also a workshop with SEG. I don't know, Jean, do you want to talk about that one?
Yeah, sure. Thanks, Eileen. So the ICG this year, I was in, October, or yeah, that was in October that we are actually have no sorry. So we are actually call for proposal, call for abstract right now, and also we expanded this topic this year that to all distributed fiber optic sensing technologies, as well as the smart city and the near environmental, near surface topics as well. So I will post the call for proposal link in the chat.
All right. So I think anything else to plug? Does
I
not.
just put the link for the roses for this year also.
Awesome. Thank you so much, Eileen. Great. So with that, we'll start moving towards a close, but I will say that once you sign out of the Zoom, you will be prompted to complete a poll we would really appreciate you filling out so we can learn or leverage this DAS RCN effort to best serve our community. So we're really looking for your input on that poll for future events or future information that you'd want to learn about DAS. So please don't close out of that window when you see it, and I will throw it back to Danica to wrap us up.
Thanks. So on a similar note, just a final reminder that the DAS RCN's Geomorphology Working Group will be holding an open community forum on June 9th. It'll be 8 to 9 a.m. Pacific time, same time as this panel. So if you're interested in continuing this conversation, learning more, providing feedback or thoughts, or getting involved with the working group, we'd love to see you there. Announcements and registration links will go out soon on the same mailing lists where this panel was advertised. And so I guess I want to thank all of our panelists, as well as Risa Madoff and Mel Zhang, my grad student, who helped us moderate the Q&A and chat. And thank you for everyone who is attending. We hope that you will be using seismology and DAS soon, if you aren't already.